Limits, the foundation of calculus. The history of limits. Limits were conceptualized in the 1800s to solidify the ideas of Newton and Leibniz. Newton and Leibniz created the ideas of calculus, which included derivatives and integrals. Limits were used to make these ideas more concrete and connect them to the already developed mathematics. It proposed finding the value of a function as it approaches some value. It's formally defined by the epsilon delta definition, where delta is made to be the interval of c minus delta to c plus delta, where c is the point you are trying to find the limit at. Epsilon is the interval of f of x on the interval of c minus delta to c plus delta, excluding possibly f of c. If epsilon can be made arbitrarily small by making delta arbitrarily small, then the limit as x approaches c of f of x is defined as the value that epsilon approaches. The concept of a limit. The limit is the value a function approaches as its independent variable, usually x, approaches some value. If the value of a function can become arbitrarily small as an independent variable becomes arbitrarily close to a value, the limit exists. Limits can be seen graphically and numerically, while they can be solved for analytically. Visualizing limits graphically. Limits can be seen graphically as the expected value of a function at a point. The limit of a function at a given point lies such that at the point of the limit you wouldn't need to lift your pencil. Limits can exist even when the function is undefined, which are at holes. The value of the limit may differ from the value of the function at a point. Graphs can only give an approximation for the limit. To find the actual value of a limit, you need to compute it analytically. Let's take the function f of x equals x cubed over 8 minus 3x over 2 plus 2. The graph's going to look like this. To find the limit as x approaches negative 2, which is right here, we look at the x value at negative 2 and draw a line directly where it intersects the graph to the right and find where it intersects the y-axis. Here we see that it intersects the y-axis at approximately y equals 4. So we can say that the limit is approximately 4. Estimating limits numerically. The limit of f of x as x approaches c can be estimated by calculating values of f of x plus or minus a, as a becomes smaller. A is some arbitrary constant. It's useful to use a table to make these estimations. Finding the average of f of x plus a and f of x minus a gives a good estimate. Generally, smaller values of a give better estimates of the limit. Let's take the limit as x approaches 0 of sine of x over x. We'll take it for these values of x. Putting it in a calculator, we get these values. We can see that this limit approaches approximately 1 because as the values become closer and closer to 0, the values get closer and closer to 1. Estimating a limit on a TI-84. It's very easy and quick to estimate a limit using a TI-84 graphing calculator. First, under y equals, input f of x. Under the window settings, make sure that the minimum x value is less than the value of c, and that the maximum x value is greater than the value of c. Otherwise, the c will not be in the range of the graph. Click Trace, then enter the value of c and press Enter. This will give you the value of the function at c. However, this is not necessarily the limit, so we're not done. Click Left to find a value that's just left of x equals c. Then click Right twice, which will bring you back to x equals c, and then move you over one place to the right, which gives us a value that's just right of x equals c. If you average these two numbers, you'll get a good estimate for the limit. The smaller the range between the minimum x and the maximum x will give you more accurate limits. I'm going to show you a quick example of estimating a limit on a TI-84. the first step is to go under y equals and enter the function that you're estimating the limit of. In this case, I'm going to find the limit as x approaches 0 of 1 minus the cosine of x divided by x. So I went ahead and entered that in. The next step is to go under the window. In this case, I'm finding the limit as x approaches 0. So we're going to enter two values for the x min and the x max that are very close to this. So for the min, I'm going to choose a value that's just less than the point I'm finding the limit at. So I'll enter negative 0.001. Under the maximum, I'm going to do the same thing, except for a value that's just slightly larger. So in this case, I'll do 0.001. After this, go ahead and click Trace. It's going to graph the graph for you. After graphing, we can see that we're at the point x equals 0. If you were finding the limit at another place, you'd want to enter that now, but we're good to go. You can see that y is undefined at this point. Even if y was defined, however, it might not necessarily be the value of the limit. What we're going to do is click left to find a value of x that's very close on the left side of the function. And then we can look at the y value for that. In this case, we get negative 1.064 times 10 to the negative fifth, which is approximately 0. It's a very small number. We now want to find a value that's directly right of it. In this case, we get 1.0638 times 10 to the negative fifth. Again, this is almost 0. From this, we can conclude that the limit of 1 minus the cosine of x over x as x approaches 0 is approximately 0. However, to find the exact answer, we would need to solve the limit analytically. One-sided limits. The left-sided limit of f of x as x approaches c is the limit as x approaches c from values of x that are smaller than c. This is denoted by putting a superscript of a negative sign on the right side of the limit. The right-sided limit of f of x as x approaches c is the limit as x approaches c from values of x greater than c, which is denoted by putting a superscript of a plus. The limit of f of x as x approaches c exists and is equal to L if and only if the limit as x approaches c from the left is equal to the limit as x approaches c from the right of f of x, which is equal to L.
So now we're going to look at an example of a one-sided limit. So the limit of x, well, x approaches negative 2 of the function of 3 when x is less than or equal to negative 2, and a function of negative 2 when x is greater than negative 2. So actually we'll be exploring this from the left side. So now we'll graph the function. Actually we'll do that in a different color. And as you can see, make the alright, now we'll actually graph it. That was the graph.
No, I'm not sure. Is that cheating? I don't understand why you tell me to shush. Stop cheating.
So 3, value of 3, x will be equal, well, x is equal to 3 all the way up to the point of negative 2. So right there. And then when x equals negative 2, well, it'll go from the point of negative 2 all the way there. Except there'll be a hole at negative 2. And as we can see, here, let me see, as we can see, as x approaches negative 2 from the left side, so it goes from there to there, the limit of x approaches negative 2 from the left side, or f of x. When f of x is 3, we can see it approaches 3. However, if we go down to the other half of the function, where f of x equals negative 2, the limit is that this would be from the right side. So if we said that was a plus instead, that would mean the limit is negative 2. And as we can see, both sides have a limit. However, together as a function, there is no limit, and the limit does not exist.
Limits that do not exist. Not all limits necessarily exist. Limits do not exist under any of the following conditions. If the left-handed limit and the right-handed limit of a function as x approaches c are not equal to each other, then the limit does not exist. If there's unbounded behavior at the point of c, the limit as x approaches c does not exist. So if the graph approaches negative infinity or positive infinity, the limit does not exist. Under oscillating behavior, the limit does not exist either, as the function is not approaching any value. Here I'll show you graphically why some limits do not exist. Let's take the limit as x approaches 0 of sine of 1 over x. We can see that as x gets closer and closer to 0, it isn't approaching any one value. In fact, the function is oscillating back and forth between 1 and negative 1. Because the function is not approaching any one value, its limit does not exist. Now let's look at this piecewise function as x approaches 1. We can see from the left, the function is approaching approximately 1.5. However, from the right, it's approaching what appears to be 1. Because they're approaching two different values, the limit does not exist, because the left side behavior, which is approaching 1.5, is different than the right-handed behavior, which is approaching 1. Now let's look at the limit as x approaches 0 of the absolute value of 1 over x. We can see as we get closer and closer to 0, the function gets larger and larger. Although there's an equal sign, this does not mean that the limit exists. In fact, the equal sign shows how the limit does not exist. In this case, it shows that the limit increases without bound. Now we'll look at a graph that doesn't experience any of these behaviors. We see this function and look for the limit at x equals 1. We can see that the function is not oscillating. We can also see that the left-bounded behavior is the same as the right-bounded behavior. They're both approaching this 1 point. We can also see that as we get close to this point, we're not approaching infinity or negative infinity. Thus, the limit does exist. In this case, it happens to be e. The properties of limits make working with limits a lot easier. For example, the limit as x approaches c of f of x plus or minus g of x is equal to the limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. This means that if you have a function that's composed of the sum or difference of several simpler functions, you can simply find the limit of those simpler functions and then find the sum or difference. This also holds true with multiplication, scalars, and division, so long as the limit as x approaches c of g of x does not equal 0, in which case the limit is not necessarily equal to this, as well as for composite functions, and to powers. This makes working with limits much simpler.
Alright, using the sum or difference property of limits, you can find that the limit as x approaches 1 of the functions x plus x squared you can say the limit as x approaches 1 of x plus the limit as x approaches 1 of x squared. That'll be squared. Then you can just direct substitute and say the limit as x approaches 1 of 1 plus the limit as x approaches 1 of 1 squared, because I substituted 1s for x's, equals 1 plus 1 squared, which equals 2. Alright, using the product property of limits, we can show that the limit of x times x squared as x approaches 1 is the same as the limit as x approaches 1 of x times the limit of x squared as x approaches 1. So then, using direct substitution, you can just say, plug in the 1 for the x's. You can just say, I keep forgetting the arrows and stuff. Oh well. You can say that 1 times 1 squared equals. I probably just make these. Using the power property limits, you can show that the limit of x cubed as x approaches 2 is the same thing as the limit of x as x approaches 2 to the third. And then, using direct substitution again, you can just go plug in the 2 for the x and say 2 to the third equals 8.
Strategies for finding limits. Limits are best solved analytically for the exact value of the solution. Direct substitution can be used if the function is continuous and is defined at the point of the limit. Dividing out cancels like terms to create a function equal to the original at all but one point, usually at the point of the limit. You can then use direct substitution to solve the new limit. Rationalization expands a rational in hopes of being able to use the dividing out method.
Using direct substitution, you can show that the limit get safe. I'll do this one in blue. Alright, using direct substitution, you can show that the limit of x over x plus 2 as x approaches 1. You can just plug in the 1 for all the x's, so you have 1 over 1 plus 2 equals 1/3. You can find limits by using the dividing out functions. So using that, you can cross out that one and cross out that one, and then direct substitute the 1 in for the x of the function that is left, and just say minus 1 equals -2, which becomes the limit of that function.
So now we're going to solve a limit analytically using rationalization. So the example we'll use is the limit as x approaches 0 of the function square root of x plus 1 minus 1 all over x. And what we'll do is we'll multiply both the numerator and the denominator by the numerator here, or more specifically the x plus 1 that's being square rooted. So we'll multiply that by the square root of x plus 1 minus 1 or plus 1, that way so we don't add any more variables to the numerator. And then we'll do the same for the denominator. We'll do x plus 1 plus 1. And now we'll multiply that together, and simplified comes out as x plus 1 minus 1 over x times x plus 1 plus 1. And as we can see, if we look, there's a plus 1 and a minus 1 in the numerator, which means that those will cancel out, which leaves us x over x times the square root of x plus 1 plus 1. And since there's two x's there, those will cancel out as well, which leaves us with 1 over the square root of x plus 1 plus 1. And now, if we think back to where x, the limit as x approaches 0, we'll sub in 0 for our x, which simplifies out as 1 over the square root of 0 plus 1 is the square root of 1, which is 1. So 1 plus 1, which is the same as 1/2.
Indeterminate forms. Indeterminate forms are those that can have different values depending on the limit they were derived from. Some common indeterminate forms include 0 over 0 and infinity over infinity. The following are not indeterminate forms, because any limit resulting in this form will only result in one answer. Plus or minus n over 0 always results in plus or minus infinity, no matter what limit it was derived from, as long as n is greater than 0. If a limit results in the form of n over infinity, it always results in 0, as long as n doesn't equal 0. Here's a quick proof of an indeterminate form, that is, of 0 over 0. We can first look at this limit, the limit as x approaches 0 of x squared over x. Using the method of substitution, we arrive at 0 over 0. The limit as x approaches 0 of x squared over x equals 0. If we use the dividing out method, we can see that this squared up here cancels with this x, resulting just in the limit of x as x approaches 0, which, through substitution, would give us 0. If we look at the limit as x approaches 0 of x over x, this also results in the form 0 over 0. The limit as x approaches 0 of x over x is 1, because we can cancel out these x's to get the value of 1. So the limit as x approaches 0 of 1 is just 1. Now we look at this limit. The limit as x approaches 0 of the absolute value of x over x squared results in the form 0 over 0. Again, we can cancel out these x's. We now get the limit as x approaches 0 of 1 at the absolute value of 1 over x. We can see that this is infinity. You may notice that these all result in different answers, even though you all received the same form. This means that 0 over 0 is an indeterminate form. The squeeze theorem. The squeeze theorem states that if f of x is less than or equal to g of x, which is less than or equal to k of x, for all x except possibly c on a range that includes c, and the limit as x approaches c of f of x equals the limit as x approaches c of k of x equals L, then the limit as x approaches c of g of x equals L. The squeeze theorem can be used when a limit cannot be solved using known methods. The squeeze theorem is only useful when the limits of f of x and k of x are equal to each other as x approaches some constant. Here's a quick squeeze theorem example. Let's take f of x equals x times the cosine of 1 over x. We know that this term right here will vary in value between -1 and 1. What we can do now is find two functions, one that is less than or equal to f of x for all values, and one that is greater than or equal to f of x for all values. We can see here that this will be true. We know that the cosine of 1 over x is going to fall somewhere between -1 and 1, meaning that at its largest, you're going to get x times 1. So, x times 1 is always less than or equal to the absolute value of x. We also know that the smallest value you could get would be -x, because the smallest value for the cosine of 1 over x you could receive is -1. This means that f of x is always greater than or equal to the negative absolute value of x. We can see this graphically here. We can see that the negative of the absolute value of f of x is right here. We can now see that the graph of the absolute value of x is right here. We know that f of x is always in between these two values, which you can see in the graph. We know that negative absolute value of x, its limit as x approaches 0, also equals 0. We can solve this through direct substitution. So we know that this approaches 0. We also know that the limit as x approaches 0 of the absolute value of x also approaches 0. According to the squeeze theorem, we know that because f of x is in between these two values, or equal to one of them, that its limit must satisfy this equation. So let's say its limit equals L. We know that it satisfies this equation. The only value that satisfies this is L equals 0, meaning that the limit of x times the cosine of 1 over x as x approaches 0 is equal to 0. L'Hopital's rule. L'Hopital's rule can be stated to find limits that result in an indeterminate form of 0 over 0 or plus or minus infinity over infinity. L'Hopital's rule states that if the limit as x approaches c of f of x equals the limit as x approaches c of g of x equals L, and L equals 0, or L equals plus or minus infinity, in other words, the limit results in the indeterminate form of 0 over 0, or plus or minus infinity over infinity, you can then use this equality, which states that the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of the derivative of f of x over the derivative of g of x. Here I will do a quick proof of the two special trigonometric limits. The two special trigonometric limits are the limit as x approaches 0 of sine of x over x, and the limit as x approaches 0 of 1 minus cosine of x over x. We can see that when we use direct substitution, we result in an indeterminate form. Let's go ahead and do it with sine of x over x. We would result in sine of 0 over 0, which is equal to 0 over 0. This means that we can use L'Hopital's rule. So let's go ahead and do that. So we know that the limit as x approaches 0 of sine of x over x is equal to the limit of the derivative of sine of x, which is cosine of x, over the derivative of x, which is 1. We can solve this using substitution. This equals the cosine of 0 over 1. The cosine of 0 equals 1, so we're going to get 1 over 1, which equals 1. This means that this limit is equal to 1. Now, let's solve the other. We can see that a similar thing happens when we use direct substitution. 1 minus the cosine of 0 over 0 equals the cosine of 0 is equal to 1, so we get 1 minus 1 over 0, which equals 0 over 0. We resulted in the indeterminate form 0 over 0, meaning we can use L'Hopital's rule. So let's go ahead and do that. The limit as x approaches 0 of the derivative of 1 minus the cosine of x, which is equal to sine of x, over the derivative of x with respect to x, which is 1. Using direct substitution, we get sine of 0 over 1, and the sine of 0 is equal to 0. So we get 0 over 1, which is equal to 0, meaning that the limit as x approaches 0 of 1 minus the cosine of x over x equals 0. Here I'll show you a quick graph of the two trigonometric limits. You can see in orange the function of sine of x over x, and in blue the function of 1 minus cosine of x over x. You can see in orange that as you get closer and closer to x equals 0, that y is getting closer and closer to 1. This agrees with what we showed in the last slide, which is that the limit as x approaches 0 of sine of x over x is equal to 1. In blue, you can see that as the graph gets closer and closer to 0, the y value also gets closer and closer to 0. This, again, agrees with what we showed in the last slide, which is that the limit as x approaches 0 of 1 minus the cosine of x over x equals 0. Continuity. Informally, a function is continuous where you don't need to lift your pencil to draw it. Formally, a function, f of x, is continuous when the limit as x approaches c of f of x equals f of c. I'll show you visually what I mean. Let's look at this graph. As I'm drawing it, I'm not needing to lift up my pencil. However, right here, there's a sudden jump in the graph. At this point, the graph is discontinuous because I needed to lift my pencil to draw it. You can see that at this point, which we will call c, the limit as x approaches c of f of x does not equal f of c. Here, f of c is defined at, let's say that this point is equal to 2. However, the limit does not even exist at this point, meaning it is not continuous. A function that is continuous on the interval a to b is continuous at every point within the interval, including a and b. For example, if we look at the open interval between here and here, every point is continuous. A function continuous on the closed interval of a to b is continuous at every point within the interval. For this, we can look from here to here. What we know here is that although the limit does not exist at the point A, the right-handed limit does exist, which is all we need in order for it to be continuous on the closed range. At B, and every point in between A and B, we can clearly see that the function is continuous. Discontinuities. A function has a discontinuity at C when the limit as x approaches c of f of x does not equal f of c. I showed this graphically in the last slide. A function has a removable discontinuity at c if the limit as x approaches c exists, whereas a function has a non-removable discontinuity at c if the limit as x approaches c does not exist. I will now show you some graphs of some functions and how we can use the graph to identify the continuity of the function. So let's go ahead and start with f of x equals 1/8 of x minus 2 times x minus 1 times x plus 2. And we can see its graph looks like this. It's a cubic function. And we're just going to be looking at the interval that the function is graphed on because we're analyzing this visually and we don't know what's happening outside of this region. So, for a function to be continuous at a point, we know that the limit as x approaches c, where c is the point we're checking for continuity, of f of x has to be equal to f of c. In other words, the value that f of x is approaching at any given point is equal to the function at that point. And so first, let's just make sure this limit exists. And to do that, we're going to first check for oscillating behavior. There's no oscillating behavior under this interval. There's no unbounded behavior. It's not approaching infinity at any point or negative infinity. And the left bound behavior equals the right bound behavior for every point. There's no point where from the left it's approaching a different value than it is from the right. So we know that this limit exists. We now need to make sure that it equals f of c. F of c is just going to tell us what the actual point of the function is. So let's take this point. We know that it's equal to wherever it is, wherever the graph of the function is. So here's the graph, and at, let's say, x equals -1, it's going to intersect the graph at this point. So that tells us what f of c is, where c equals -1. The limit is just a value that the function's approaching at that point. And we can see that it is approaching that pink dot, which is f of c. So we know that these are equal, at least at -1. Now we could do this at any point on this graph, and we'd find the same thing. And so that means that the function is continuous, at least on this green range. So we can say that this function is continuous. Now let's take the function of f of x equals -x cubed over 2x plus 2. Here's a graph of it. And so you could follow the previous steps to find if the limit exists, and that's true. There's no oscillating behavior, no unbounded behavior, and the left-sided and right-sided limits at every point are equal to each other. But now you can see we have this hole on this graph. Here, so at f of 0, this is undefined. Does not exist. Undefined. And so what that means is f of 0 doesn't exist. There's no value for it. Now we can find the limit right here, and we can see, so let's take the limit as x approaches 0 of -x cubed over 2x plus 2. This x is going to make this 3 at the top turn to a 2. You're basically just canceling out an x on the top and the bottom. And so then that's going to be equal to the limit as x approaches 0 of -x squared over 2 plus 2. Can fill in the x with a 0, and so then you're going to get -0 squared over 2, which is just 0. So you're basically going to end up with 2. So the limit at this point, at x equals 0, is going to be 2. Well, the function is undefined at that point, and 2 does clearly not equal undefined. So we say at x equals 0, there is a removable discontinuity. And the reason there's a removable discontinuity is because the limit at this point exists. If it did not exist, we would say it has a non-removable discontinuity. Essentially, a removable discontinuity means that if we redefine this function, and so we said this function, so let's say the new function is called g of x, and we're going to let g of x equal f of x for all points, except when x equals 0, g of x, so g of 0 equals 2. So it equals the value that this limit is approaching. And so if we looked at g of x, its graph would be completely continuous, because the graph would look like this. There would no longer be a hole right here, because we're saying that the function is defined at that point, and it's equal to the value it is approaching, its limit. Now let's look at another function, a piecewise function. F of x equals x squared over 2, where x is less than 2, and f of x equals -x squared over 4 plus 4, where x is greater than or equal to 2. here we can see there's a jump in the graph. And so we could follow the same procedure. We know that on this range, there's no oscillating behavior, there's no unbounded behavior, but right here, there is a different left and right bound behavior. From the left, we're getting closer and closer to this value, whereas from the right, we're getting closer and closer to this value. And you can clearly see that this red line and blue line are different values, meaning that the left and right bound behavior is different at that point. So we know that the limit exists at every other point. We can see that there are no holes in the graph, meaning that at every other point, this function is continuous. But we need to now look here. The limit here is undefined. In the last problem, we saw that the function was undefined. Here, the function is defined. At x equals 2, it's defined as this. So we're going to get negative 2 squared. That's going to be 4. So negative 4 over 4. That's going to turn into a 1. So we have negative 1 plus 4. So that would just give us 3. And so we know right here that equals 3. The function is defined. But we need to say that 3 equals the limit as x approaches 2 of f of x. And that is not the case, because this limit right here, it doesn't even exist. And 3, it cannot be set equal to something that does not even exist. So what we say here, because the limit doesn't even exist, is that there's a non-removable discontinuity. In other words, when you're looking at a graph, if you see holes, that represents a removable discontinuity. If you see jumps, that's going to represent non-removable discontinuity. And when there are neither, that's going to represent where the function's continuous. You can actually see on these graphs, at pretty much every point, the function is continuous. The only points where it's not is where there's the jump and when there's the hole.
Let's say we are asked to determine the continuity of a function based on a graph we have depicted here. So, we'll call this value, this x value, c. As you can see, the graph approaching from the left has a y value there at x equals c. And when you're approaching from the right, it has a y value of here. Based on this, we can determine that the graph is not continuous because approaching from the left and from the right, the value at c is not equal. Again, we are asked to determine the continuity of a function based on a graph. The graph we have is a cube root function that looks something like this. Based on the graph, we can see that there are no holes anywhere, and there are also no asymptotes. Also, it is not oscillating, such as a function like this, where it oscillates too many times back and forth to determine the limit. And with an asymptote, say the asymptote is at this c value, we don't have a function that goes to positive or negative infinity in either direction. So this function is continuous.
The intermediate value theorem. The intermediate value theorem states that if a function, f of x, is continuous on the closed range a to b, then f of x equals c for all c that are in between f of a and f of b on the range a to b. Let's take f of x equals x squared over 4. I'll show you graphically what I mean. Here's a graph of the function. We know that f of x is continuous on the closed interval 0 to 4, as, if I sketch over this, at no point do I need to lift my pencil while I'm drawing it. We know that f of 0 equals 0, and that f of 4 equals 4. So we have this range of f of x on this interval. What the intermediate value theorem says is that there is a c that exists such that f of x equals c for all c in between 0 and 4. So let's say we wanted to find when c equals 2. The intermediate value theorem says that this exists because 2 is greater than or equal to 0 and is less than or equal to 4. So, looking at this graph, we know that it would lie somewhere right about here. The intermediate value theorem doesn't tell you where this value will exist, but it does tell you that it does exist. All we know is that it lies somewhere in the interval from 0 to 4. Existence theorems. Existence theorems show that some function, f of x, is equal to a constant, c, at some point. It doesn't tell you what x is when f of x equals c, nor does it tell you how to find it. Some examples of existence theorems are the intermediate value theorem, which I went into detail about in the last slide, the fundamental theorem of algebra, which states that a polynomial of degree n has exactly n roots, and the mean value theorem, which we will learn about later in the derivatives unit. Infinite limits. If, as x approaches c, f of x increases or decreases without bound, it is said to have an infinite limit at x equals c. An infinite limit shows that at c, there is no limit. At an infinite limit, there is a vertical asymptote. If the limit as x approaches c results in a over 0 through direct substitution, f of x has a vertical asymptote at c, where a does not equal 0. Infinite limits graphically. In the last slide, I explained infinite limits to you, but it's a lot easier to understand if you view them graphically. Let's take the function f of x equals 1 over x. Here's a graph of it. As you can see, from the left, the function gets smaller and smaller and smaller. It's approaching negative infinity. From the right, the function is getting larger and larger and larger. It is approaching positive infinity. We can write this like this. Now, don't be confused. Although there are equal signs, it does not mean that the limits actually exist there. In fact, by saying that it equals plus or minus infinity, it's showing that the limit does not exist. As hopefully you can recall from previous slides, a limit does not exist if it increases or decreases without bound. In this case, from the left, the function is decreasing without bound, whereas from the right, the function is increasing without bound. This means the limit does not exist. However, there is a vertical asymptote at x equals 0. A vertical asymptote is where there is a line going vertically that the function approaches but never actually touches it. Now let's look at the function of 1 over x plus 1 squared. Here's a graph of it. Here, from both the left and the right, the function is approaching infinity. We can write that as this. Again, do not be confused by this equal sign. This limit does not exist, as it increases without bound. Here, there's a vertical asymptote at x equals negative 1, which we can see here. You can see the lines getting closer and closer and closer to it, yet they will never touch it. Limits and derivatives. Limits can be used to find the derivative of a function. In fact, limits were largely conceptualized in order to solidify the idea of a derivative. The derivative of a function is the slope of the tangent line to each point on the function. The derivative of a function f of x with respect to x can be shown as the limit as change in x approaches 0 of f of x plus change in x minus f of x divided by the change in x. We can view this by looking at a graph of a function. Here's one. If we take 2 points, it's easy to find the slope between them. What the derivative does is it finds, as these 2 points get closer and closer together, it finds the limit when the points overlap each other. There's 0 distance between them because the change in x approaches 0. At this point, at this limit, we find that instead of a secant line to the graph, it becomes a tangent line because the graph only touches the line once. Here, we define this to be the derivative of the function, and it gives us the slope of the tangent line at each point of the function. Here I'll show you an example of finding a derivative using limits. Let's find the derivative, or in other words, the slope of the tangent line of x squared at any given point. First step is to write using the limit notation. So we have the change in x as it approaches 0, or delta x, and that is of f of x plus delta x minus f of x over delta x. We know that f of x equals x squared, so I'm going to go ahead and fill that in. That'll give us the limit as delta x approaches 0 of x plus delta x squared minus x squared over delta x. I'm now going to go ahead and expand this. So that's going to give us the limit as delta x approaches 0 of x squared plus 2x times delta x plus delta x squared minus x squared all over delta x. Now, here we have a x squared, and here we have a negative x squared. So those are going to just go ahead and cancel out. Now, what I'm going to do is I am going to factor out a delta x in the top. You can see that here we have a 2x times delta x. That delta x is being factored out. And here we have delta x squared, which we can rewrite as delta x times delta x. One of these delta x's is being factored out, and the other one will be left. So we'll have this. And in the bottom, we still have delta x. Now, these two are just going to head and cancel out. So we now have the limit as change in x approaches 0 of 2x plus change in x. Using direct substitution, we have that equals 2x plus 0, which is equal to 2x, meaning that the derivative of x squared with respect to x equals 2x. So if we look at a graph of y equals x squared, if we look at a point, let's say we look at the point x equals 1. At that point, the slope of the tangent line here is going to be 2, because x equals 1, and we have 2x, so 2 times 1, that's going to give us 2. And there we found a derivative using limits. Limits and integrals. Limits can be used with Riemann sums to find the definite integral of a function over some interval. The definite integral of a function, f of x, is the area underneath the curve of f of x bounded by the lines x equals a, x equals b, and y equals 0. Note that any area underneath y equals 0 is treated as negative area. Let me show you an example. let's say we have a graph of this function, and we want to find the area underneath the curve from here to here. What we're going to do is divide this region into a bunch of rectangles to estimate the area. This isn't going to give us the perfect amount of area. As you can see, there's a bunch of areas like right in here, here, here that are all not being included. But this will give us a fairly decent estimate. Now, if we make these rectangles smaller and smaller in width, it's going to give us a more accurate measurement. Oh, and actually, you would not be taking these rectangles into consideration. What we can say is that the definite integral of a function, f of x, from a to b is equal to the limit as n approaches infinity of the sum, where I starts at 0 to n, of f of c sub I times change in x times b minus a over n. B minus a, as we showed, is just the interval where we're taking the area of. Delta x is going to be the width of the rectangles. And f of c sub I is going to give us the height of the rectangles. So right here is giving us the area of the rectangles. And this is basically going to give us the exact area underneath the curve because we are taking an infinite amount of subintervals. Here I'll show you an example of finding the area underneath a curve, or the definite integral, using limits. So we want to find the indefinite integral from 0 to 1 of x cubed with respect to x. So what that means is we are just going to be looking at this graph, and we want to find the area from 0 to 1. So we want to see what is the area underneath this curve. So all the area inside of here. And so we know that this is going to be equal to the limit as n approaches infinity of the sum from 0 to n of, we have the function of c sub I, and that's going to give us the height. We have, then this is multiplied by change in x. This is going to be giving us the width. So together, these give us the area. And then we have over the interval it's on. So that's going to be b minus a. And we know that b is 1, a is 0, so this is going to be just 1. And since it's multiplication, anything times 1 is itself, so we can go ahead and cancel this out. And this is going to all be over n, the number of subintervals. So essentially what we are doing here is we are dividing this into an infinite number of rectangles and adding all of the areas of those infinitely small rectangles together to find the area. So let's go ahead and begin. So we can rewrite this as the limit as n approaches infinity of the sum, where I starts at 0, goes to n, that's a 0, I'm sorry. And we can write this as I over n, so I is going to be basically the height of the function over n, the number of subintervals, and we have x cubed, that's our function, so this is going to be cubed, and then it's going to be multiplied by 1 over n because, well, we still have this n, the number of subintervals, so we go ahead and multiply those together. And so, looking at this, these n's are all constants, and so we can just go ahead and pull them out of our sum. So we have right here, this is equal to 1 over n to the third, and it's multiplied by 1 over n. So that's going to give us 1 over n to the fourth. So we're going to pull out 1 over n to the fourth, and we still have this sum of I cubed. And we know what this is. And we know that that is equal to n squared times n plus 1 squared over 4. I'm not going to prove that now, but we mathematicians have figured out that that sum is equal to this. And this n, where this n is coming, these n's are coming from right here. Okay, so now we can simplify this further, and we now have the limit as n approaches infinity of 1 over n to the 4 times, now I'm going to go ahead and expand this out, so we're going to have n squared times n squared plus 2n plus 1 over 4, and that's going to give us the limit as n approaches infinity of 1 over n to the fourth of n to the fourth plus 2n to the third plus 1 over 4. We can rewrite that as 1 over the limit as n approaches infinity of 1, because n over 4 divided by n over 4 is going to give us 1 over 4. So no, that won't be 1. It'll be 1/4. And then we have plus, we have 2 fourths, so 1/2 times n3 over n4. So that will give us 1 over 2 to the nth. And then we have plus 1/4 times 1 over n to the fourth. So 1 over 4 n to the fourth. Well, we know that both of these are going to approach 0 as n approaches infinity, because we get 1 over infinity. So cancel these, and we simply get that the limit equals 1/4. So we now know that the area underneath this curve is equal to 1/4. End behavior. Limits can be used to determine the end behavior of a function. The limits as x approaches plus or minus infinity is considered the end behavior of the function. If the limit as x approaches plus or minus infinity of f of x is bounded and equal to L, then L is a horizontal asymptote of f of x. Now let me show you a graph of what end behavior is. So let's say we have the function 1 over x. Well, as we've seen before, there is a vertical asymptote at x equals 0, because the graphs get closer and closer and closer to that line, but they never touch it. But what if we want to find a horizontal asymptote? It looks like there might also be one along here, as the graph seems to be getting closer and closer and closer to this line, but never touching. And that's what we call end behavior. Essentially, as this graph goes farther and farther on, what value is the function going to be approaching? So basically what we have is the limit as x approaches infinity of 1 over x, and this is just going to result in 1 over infinity, and that simplifies to 0. So we know that going to the right, going this way, the function is going to approach 0. And we can do a similar thing by taking the limit as x approaches negative infinity of 1 over x. And that is going to give us 1 over negative infinity. And that also equals 0. So when we go to the left, an infinite amount, we will be approaching 0. Meaning that at the line of y equals 0, there is a horizontal asymptote. Here I'll show you an example of end behavior. So let's take the function f of x equals x. Here is a graph of the function, and we want to find the end behavior. Now, it looks like as we move to the right, we are getting closer and closer to infinity. Whereas when we go to the left, it looks like we are getting closer and closer to negative infinity. So let's go ahead and take the infinite limit to find out if we're correct. So we are going to take the limit as x approaches infinity of x. And using substitution, we get that it equals infinity. So it does in fact increase without bound to infinity. Now let's see if we're right moving to the left. The limit as x approaches in negative infinity of x is going to give us negative infinity, meaning that it does in fact decrease without bound as x approaches infinity, negative infinity. Now, if we look at a different graph, let's say f of x equals 1 over x squared. This graph is going to result in something like this. So what's the end behavior of this? It doesn't look like this is moving down very much. It doesn't look like it's going to approach negative infinity. It certainly isn't moving up, so it's probably not going to approach positive infinity either. So let's take the limit. So we're going to take the limit as x approaches infinity of 1 over x squared. And that's going to give us 1 over infinity squared. And that just equals 0. And we can do the same thing going to negative infinity. So x approaches negative infinity over 1 over x squared. And that's also going to give us 0. So it means that as we move in either direction more and more, we are going to be approaching 0. Because of this, we never actually reach 0 and we never go below 0. There is going to be a horizontal asymptote at y equals 0. Indefinite integrals. Indefinite integrals are those that cover an infinite area. So, for example, we can say the integral bounded by 0 and infinity of f of x. This is going to be taking a, it's going to be, if we look at the graph of this, it is going to be taking the area underneath all of this all the way to infinity. So there's an infinite amount of space underneath the graph that the area is being taken under. To solve indefinite integrals, you need limits because you can't work directly with infinity without using limits. Many indefinite integrals are in fact infinite, although sometimes the integrals do converge and the area is actually finite. Here I will show you an example of solving an indefinite integral which requires the use of limits. So let's look at the indefinite integral from 1 to infinity of 1 over x squared with respect to x. And so just to show you a graph of what this is kind of going to look like is, so if here is 1, we want to find the area underneath here all the way to infinity. And it looks like it's going to have an infinite area, but we're going to go ahead and solve this indefinite integral and see what it actually comes out to be. So we're going to go ahead and rewrite this integral as x to the negative second. This is just going to make it easier to work with because it is more like a polynomial. And so then we know that this is going to equal negative 1 times x to the negative first from 1 to infinity. And we can rewrite that as negative 1 over x from 1 to infinity. So now comes the hard part. How do we write this? Normally, if this was negative 1 over x from a to b, it would simply be negative 1 over b minus negative 1 over a. However, how can we do this with infinity? And what we're actually going to do is we are going to take the limit of this part right here. So we're going to have the limit as x approaches infinity of negative 1 over x minus negative 1 over 1. So basically just plus 1. And now we are going to solve. So the limit as x approaches infinity of negative 1 over 1, that's going to give us negative 1 over infinity, which equals 0. So what we're going to have is 0 plus 1. And that's going to give us 1. So what this is telling us is that all this area highlighted in red over here, even though we're taking it over an infinite interval, all of that area totals to just be 1, which I find to be pretty neat.